welcome our LCN colloquium speaker today, Professor Jason Petta from Princeton University. Jason did his PhD at Cornell, already looking at quantum dots and spectroscopy and transport, and then moved to do a postdoc at Harvard, working in a group with Charlie Marcus, performing some seminal experiments on moving into the time domain and dynamics of double quantum dot systems. And indeed, in the field, most talks now begin with the so-called Petta slide or Petta paper, sorry to embarrass you, outlining those types of single triplet dynamics. So we're delighted to have Jason here talking. So since then, he then moved to set up his group at Princeton, and we're going to be hearing about some latest results there on coupling now some of these quantum dot spins to light and through resonators. Thanks very much.
Good. Thank you for the nice introduction and for having me here, giving me the opportunity to speak. Can you hear me in the back? Is this loud enough? It's my first time in London, actually. And next time I come back, I'll have to stay a little bit longer. But I had a little bit of fun wandering around town and checking things out, and appreciate the invitation and the chance to speak here. I want to tell you about some work that we've been pursuing at Princeton for almost 6 or 7 years. It's one of these projects that sort of nucleates the crazy idea. You put a student on it and see whether it takes off or whether it tanks, right? And this is a project that recently has taken off on a really nice trajectory. What we're trying to do, the vision of the project is to eventually try to entangle 2 electron spins that are separated by a distance of order a centimeter using single microwave frequency photons. And this field of research kind of lies at the intersection of superconducting qubits and semiconductor spin qubits, but really what we're after is sort of cherry picking the best ideas from these 2 different fields and putting them together into a new sort of hybrid technology that uses light to couple quantum objects and uses light for quantum measurements, but does these experiments in a very clean material system that can be isotopically enriched and lead to very long quantum coherence times. So just in terms of background, are any of you in bio or other areas of physics, sort of a nanoscale colloquium? So condensed matter crowd, more or less? Okay. So, so generally, I think what kicked off our field of quantum information science and technology is the idea of using qubits, quantum 2-level systems for quantum algorithms. And this is largely motivated by Shor's algorithm for factoring. This is a long-term project, right? I mean, it's something that's going to take decades of pursuit to get to this end game. But I think, as students kind of coming into the field, new postdocs, maybe what you're seeing now is that there are other types of quantum technologies that today I think are having an impact on daily life. And one example of this is quantum sensing. The idea of using these, very sensitive quantum states, spin states of, say, nitrogen, vacancy center, and diamond, to probe materials, real material systems, condensed matter systems, to probe biological systems, due to the extremely high sensitivities that they allow us to have. And so this is a very rich field, with a lot of people pushing toward this end game of building a scalable quantum computer. But I think there are a lot of sort of road stops on the way to that are nice and are producing a lot of good physics and a lot of good technology. Okay. So it's an exciting time to be a grad student and a postdoc in this field. I mean, one of my students just took a position at Google. There's sort of jobs in quantum technology that were not available 10, 15 years ago, I would say. Okay. So in terms of quantum computing hardware, there are many different ways to work with these systems. You basically want an experimentally controllable 2-level system. Many of the early experiments were done with liquid-based NMR, and there have also been very successful approaches based on trapped ion, cold atom systems, Crispin Rowe, David Wineland, Rainer Blott, those groups. There's, I think, a lot of work here in the UK on optical-based quantum computing. And then all these technologies below, you could maybe, if you're generous, classify as semiconductor-based technologies, because even the superconducting qubits, are based on silicon wafers or sapphire substrates. But the idea is to use, Cooper pairs, quantum states of electrons and superconductors to implement a qubit. There are new approaches based on topological states of matter that might give you protection against decoherence that can lead to long coherence times. So this is an emerging field of topological quantum computing. What I'm going to focus on in the talk today is, the spin-based quantum computing. We're going to try to use the spin state of single electrons as our degree of freedom to make our quantum bit. Okay, that's what we work on in my group. But let me just give some background in terms of basics. Semiconductor spin qubits come in a few different flavors. The simplest kind of qubit is what's called the Loss-DiVincenzo qubit, proposed by Loss and DiVincenzo. This is just what you might imagine. You take one electron, trap it somehow in space, and then apply a large external magnetic field so that the spin up and spin down states are split by the Zeeman energy. And then these two states, right, spin up and spin down, are simply going to encode your qubit state 0 and 1, right? And so this is a nice approach because you can just use the standard toolbox of electron spin resonance to manipulate these single spin qubits. There have been additional proposals since this early Loss-DiVincenzo proposal to implement different types of semiconductor spin qubits. Another type of qubit is based on what's called 2 electron spin states, so singlet and triplet states. And for singlet and triplet states, you basically have 4 energy levels that you can work with. This is the m sub s equals 0 spin singlet state, the m sub s equals 0 spin triplet state, and then you have the polarized triplet states, where this spin is up and this spin is up, or this spin is down and this spin is down, the up, up, and down, down states. And the idea of this qubit is to work at a finite magnetic field so that you push the up, up, and down, down states off by Zeeman energy and kind of get them out of the picture. And then you're just left with a 2-level system here consisting of the m sub s equals 0 singlet and triplet states. And so, you might ask, why would you bother doing this? What's the motivation behind, making a more complicated system? If you could use 1 electron, why use 2? Right? But the idea is that in this system, the m sub s is equal to 0, so these 2 states, singlet and triplet, will not couple to overall magnetic field fluctuations. And that gives rise to what's called the decoherence-free substrates that, in theory, should give you kind of longer quantum coherence times. And there are more recent examples of 3 electron spin qubits and so on and so forth. I'm mainly going to focus on this kind of flavor of qubit in today's talk, the simplest single spin qubit, and how it interacts with light. All right, so David DiVincenzo is probably the first person to really step back from a high level and think about what you would need to do to make a realistic quantum computing system. Right? You need to be able to initialize your state, read it out, perform some universal set of gates. Ideally, you would do this in a scalable system with long quantum coherence times. And what Loss-DiVincenzo did a long time ago was to think about a specific physical implementation, a specific physical system that would allow you to make a quantum computer based on the spin degree of freedom. And I think what's pretty remarkable is that there's been sustained effort in this area of research, and many of these individual criteria have been kind of checked off for electron spins and semiconductors. For example, if you have a single spin qubit and you want to initialize it in a well-defined state, you can just simply go to high magnetic fields and let the system thermalize so that the system ends up in the ground state. Right? So it just sits there. You can do spin initialization. Elzerman's here did some early work on spin-to-charge conversion and using charge detection and some spin-dependent tolling event to actually read out spin states, or Pauli exclusion principle. And then for quantum control, the idea is to use electron spin resonance for single spin rotations. And to implement a 2-qubit gate, you can momentarily push those 2 electrons together, make their wave functions overlap, and turn on what's called an exchange interaction. But you can cause those 2 spins to interact with each other in a time-controlled manner. And what's really nice about this system, and John's done a lot of seminal work in this field, is that if you work with the right semiconductor, you can have extremely long quantum coherence times. That approach time scales that you might only see in, say, a trapped ion system. And so one of the things that we're working on hard at Princeton is trying to take these early gallium arsenide spin qubit experiments to cleaner material systems that are more supportive of long-lived and sustained quantum coherence times. Okay, good. All right, so the single qubit operation is just based on electron spin resonance. A 2-qubit operation is based on this exchange coupling. And one of the limitations of exchange coupling is that it's a very local interaction. If you want to have these 2 spins interact through exchange, then you need to push them together on a 50 or 100 nanometer length scale and momentarily make their wave functions overlap. And this requires a lot of control over these individual wave functions, right? So you're forced to live at this small length scale to do this effectively. And this is work from gallium arsenide. There's more recent work in the past year from our group here at Princeton, and also the Delft group, kind of demonstrating this again in the silicon system. But exchange interaction by nature is a very local kind of quantum operation. These 2 spins need to basically be right next to each other if you want to do that. And so what I want to talk about today in this colloquium is what we can do to move beyond a kind of nearest neighbor type interaction for electron spins and semiconductors, and to throw a few ideas out there about how we could possibly do that in the laboratory. Let me explain first why you might want to have some kind of long-range spin-spin coupling instead of just a short-range nearest neighbor kind of interaction. This is a nice group from Chris Monroe's group at University of Maryland, and his group traditionally works on trapped ion systems, but you might be aware that IBM recently has had 5 qubit processors and larger processors that you can access online on the internet and actually program and run. And Chris's group did that. They benchmarked some kind of standard quantum algorithms. This is a Toffoli gate. It's a control not operation. There's a hidden shift operation that sort of looks at a shift of a state in the input register and tries to determine what that shift is. But what they did is they compared the performance of the trapped ion system to the superconducting system. And yes, these systems are different in terms of the way they're made, but there's a more kind of deeper quantum information difference that's important. And this is called connectivity and how these qubits are actually connected together. The trapped ion system is based on a collective vibrational degree of freedom, and that system gives you what's called all-to-all connectivity. If you look at their 5-qubit system, any qubit in a 5-qubit system can be coupled to any other qubit in that system, and that gives you this all-to-all connectivity. Whereas for the IBM superconducting processor, they kind of had one central qubit in the star configuration, and that qubit could only couple to sort of nearest neighbors, right? So this is a direct way to stack up a kind of nearest neighbor coupling to a fully connected, or what's called an all-to-all coupling. And what they show in this paper is that there are certain algorithms that are based on kind of large-range entanglement, and there are other algorithms that are very local, that just rely on nearest neighbor operations. And you can see, for example, for the trapped ion system, the hidden shift algorithm, which relies on a lot of entanglement, has a much higher fidelity than the superconducting qubit system, which only has like a 35% fidelity, just due to the way the algorithm is actually implemented in hardware. So from a hardware level, this is kind of an ideal to aim for, is a system that's fully connected so that you can actually generate entanglement or create entanglement between any 2 qubits on the chip and not have to sort of shuttle or transfer entanglement through intermediate qubits, which is sort of what's done in this system. Okay? So that's a specific example. This is a more kind of down-to-earth example that we build devices in the laboratory. They're never perfect, and there are always issues. And so this is a device I'll talk about later. It's a spin chain of 9 quantum dots that are nearest neighbor coupled together. If you have any kind of defect in the system, the spin chain, it's just going to end your experiment. You're not going to be able to build a larger processor or a larger chain and take advantage of that if there's an error someplace in the middle. And so being able to get kind of out of the plane, right, to have something beyond nearest neighbor is helpful. There are other engineering-related reasons for wanting to have a long-range spin-spin coupling. In the end, we'll probably have some kind of modular device architecture, right, with local processors that are connected together. And it'd be nice to be able to do that chip to chip, or maybe even cryostat to cryostat. So really what we're lacking with spins is a way to couple things long range over relatively large distances, right? We're sort of stuck to this 50, 100 nanometer length scale. Okay, here's some routes that have been explored so far to implement long distance coupling of spins. Some of these are theoretical. This is a theoretical proposal from a group at UW-Madison. This is Mark Erickson, Sue Coppersmith, and Mark Friesen. And the idea is to have a coupling between 2 spins that are very far away by using intermediate exchange coupled spins. So this is it's called the spin chain. It's many spins connected together. Each spin is connected to its neighbor to the left and right. And what they show theoretically is that if you can actually build this system in the laboratory, you would have an effective exchange coupling between the first and last spins. And that exchange coupling would go like the nearest neighbor coupling divided by square root of n, right? So in theory, you could do this. Someone has to make this, right, and make it work. That's kind of a challenge. At the end of the day, you're going to be stuck with problems like this, right? If there's a problem in the middle of your device, this kind of long-range coupling doesn't work. This is a little bit closer to home. This is an experiment done in the UK of using surface acoustic waves to try to physically transport an electron in a moving electrical potential that's generated by an acoustic wave. It's a really impressive experiment where there's a quantum dot here and a quantum dot there, and the sample was hit with what's called a surface acoustic wave. It's a vibrational wave. Due to the nature of this material, it's piezoelectric, you can set up a moving potential, and you can actually transport that electron across the chip in about 50 nanoseconds using this potential that's generated by the sound wave. And they did this very nicely. They played a ping pong with a single electron and showed that they could kind of whack it back and forth across the device, many, many times and not lose it, right? So you can imagine approaches like this. But it's maybe hard to think about scaling this up to a 10 or 50 qubit system where you want to move electrons in different directions, right, on the chip. Okay. So the approach that we're thinking about leverages some of the ideas that have been explored and developed in the superconducting community for about 10 or 15 years. And instead of trying to physically transport the electron, what we want to do is couple or transfer the coherence of the electron spin state to a different quantum degree of freedom that can more easily be moved around on chip. And this has worked out very well for the superconducting qubit community. This is an early paper from Rolf Scholkoff's group where they took a superconducting cavity and trapped microwave frequency photons in it, and they showed that they could get those photons to coherently interact with a single superconducting qubit, and that results in what's called vacuum-Rabi splitting, a real sort of hybridization of light and matter, but at the single particle level. Okay. What's nice about this ability to couple light to a qubit is that you can also use the same coupling to couple one qubit that's on one side of this device to a second qubit that's all the way across the device, about a centimeter away. And this was directly explored a few years later in this experiment where they showed that you could have a coupling between two qubits that's separated, on a centimeter, millimeter type length scale. And this coupling is mediated by a photon, by light, which bounces back and forth and then mirrors between this cavity. And what we're after in my group now is a demonstration like this, but for single spins that are trapped in semiconductor quantum dots. Okay. So one question you might ask is, why is this so hard? Why hasn't it been done? This idea of using microwave, for example, to couple spins together. And the issue is just kind of energy scales. The magnetic field that's generated by a single photon in one of these microwave cavities is on the order of a nanotesla or a tenth of a nanotesla. And if you just calculate the alarm or precession frequency in that small field, it's about 10 hertz. That would be the clock speed of your quantum computer, right? Very, very slow. And in principle, 10 hertz is slow, but it's also much, much slower than decoherence times that we have in typical devices. So you can't really do anything quantum at this very low speed. And several approaches have been pursued. These are some of the early papers, and there's been a lot of work in this area of using spin ensembles, large spin ensembles, to couple the microwave frequency photons. And what happens with large spin ensembles is that you end up with a kind of root N enhancement of the coupling rate, and you can push this up into the 10 megahertz range just by working with a larger system size. What my group likes to do is we like to work with single spin degree of freedom. And you can see from these numbers that it's going to be quite difficult to demonstrate anything that's quantum mechanically coherent if you can just have a 10 hertz coupling rate. So I'm going to tell you today about a new way to couple spin to light and show you that we can coherently couple a single photon to a single spin. And the key ingredients of this experiment is we're going to take a silicon quantum device that we can trap a single electron in a double well potential. And we're going to use the field gradient that's generated by a little micromagnet, and we're going to move the electron around in that field gradient so that the Zeeman energy of that electron depends on position. Okay? And what this does is this creates what's called spin-orbit coupling, or you can think of it as a spin-orbit coupling. It couples the spin of the electron to the orbital degree of freedom, or its momentum, right? And the combination of spin-orbit coupling and kind of standard electric dipole coupling between the charge of that electron and the electric field of the cavity will actually, in the end of the day, it will couple the spin to the photon. Okay? So it's an indirect coupling process. It's not a direct magnetic coupling process like this rate is, but it's an indirect process that uses a large electric dipole interaction plus a spin-orbit interaction to kind of bridge the gap, right, to achieve the spin-photon coupling. Okay? So I guess here's the roadmap for the top. I want to tell you a bit about how we make the devices in silicon and kind of what the key hurdles were to get these devices to work. And I'll talk about a set of experiments where we started to combine elements of the semiconductor spin qubit field with the superconducting qubit field. And we call these hybrid devices or super semi devices because these devices incorporate superconducting elements and semiconductor spin qubit elements in a nice way. And once these devices started to work, we could really dig into the physics, some basic physics of light-matter interactions. First demonstration of this is what's called charge-photon strong coupling. I'll show you that we can couple the charge of a single electron to a single photon that's trapped in this cavity and do that in a coherent way. So that the interaction rate between the charge and the photon exceeds all the velocity rates in the system. And I have to admit, it wasn't obvious that this would work, just given the relevant timescales for charged qubits and semiconductor devices. Okay, so it's nice that this is working in silicon. I think what's even more impressive or optimistic in terms of moving forward the field is that we can extend this work of the charge-photon coupling. We can include this ingredient of the spin-orbit interaction, and we can actually coherently couple a single electron spin state to the electric field of a single microwave frequency photon. And this sort of just directly pops out at you in the data. You really see the hybridization of these two different degrees of freedom, the spin state of that electron and the single photon that's trapped in the cavity. Okay, so that's where we're headed. Let's kind of dig in and talk about public enemy number one for our field, which is just decoherence, and how it rears its head for spins in semiconductors. This is a really elegant picture from DiVincenzo, shared it with me, of their architecture for single spin qubits and gallium arsenide. The idea at a theorist level is that you have some parabolic confinement potential, you trap an electron in it, you work at high field, and you control the spin, and that's your spin qubit. But if we put on our condensed matter physics hat, we know that that electron's not in a vacuum. It's sitting in a host lattice, either silicon or gallium arsenide. It takes on the G factor of that host lattice. It takes on the effective mass of that host material. And moreover, those lattice nuclei can carry spin. And in the case of gallium arsenide, all of the lattice nuclei in the substrate have nuclear spin 3/2. Now, from a quantum level, we think about one spin in a large magnetic field. There's some Zeeman splitting and a Zeeman interaction, B dot S. But what happens is, due to this hyperfine interaction, an electron trapped in a quantum dot also sees a small field contribution from each nuclear spin that wave function overlaps with. Okay? So you have extended wave function. It's about 50 nanometers across. Okay? And it's overlapping with about 1 million lattice nuclei. And you can sum over all those lattice nuclei and calculate what the effective magnetic field is. And the surprising thing for gallium arsenide is if you were to fully polarize those lattice nuclei, this is a huge effect. It's a 5 Tesla magnetic field. It's the equivalent of a 5 Tesla field. It's massive. And even in a situation where the nuclei aren't polarized, you still have a couple of millitesla random fluctuating, RMS scale field. And if you convert that into time, that implies about a 10 nanosecond decoherence time. Okay, so that's the groundwork for gallium arsenide. So there are a couple of ways to deal with this. One is to try to polarize the lattice nuclei so that they're not fluctuating. And Amir Yacobi's group and other groups have looked into that. The approach that we're taking is just to jump ship and leave 3.5 behind and move to a different material system. And the material system that we selected, and I think the community at large is kind of headed in this direction, is silicon. One reason is just mass production works well with silicon devices, and so if we can make a few qubits work well, the hope is that this is a technology that could just quickly blow up into a much larger system size. Main reason for switching from 3.5s to silicon is just coherence. And this is a theoretical prediction from Shankar Sharma's group. It shows the coherence time, I don't know if you can read that in the back, as a function of isotopic enrichment of silicon. Right? So silicon has 3 naturally occurring isotopes, silicon-28, silicon-29, and silicon-30. And silicon-29 is about 5% in natural abundance. That's the only spin-carrying naturally abundant isotope in silicon. Okay? So if you start at natural silicon, have a T2 that's maybe 10 microseconds. But as you increase the isotopic purity and get rid of more of the unwanted, bad actor silicon-29, the coherence time, in theory, will just grow and grow, and you're expected to see T2's coherence times that are on the order of seconds. So, fortunately, there's a project in the EU to make a kilogram standard out of silicon to make this bowling ball. And little offcuts of this ball from what's called the Avogadro project ended up in John's lab and Steve Lyon's lab and Mike Thewald's lab, other labs throughout the world. And some scientists did measurements on those. And the neat thing is that if you really measure T2, this is real theory and it works. And you can have coherence times in isotopically enriched second, silicon that approach second long time scales. This is another experiment from Mike Thewald's group, a few years back, where they took isotopically enriched silicon, I think it was doped with phosphorus, and they did a process called electron nuclear double resonance, where you can transfer coherence from electron spin state to the nuclear spin state. And they showed that they could make a quantum memory that had a lifetime of, I think it was like 40 minutes at room temperature and several hours at low temperature, right? So all of a sudden, this is real. And in a solid state system, we have access to coherence times that I think you'd only see in sort of trapped ion systems, right? Extremely clean, ultra high vacuum conditions, and in our dirty semiconductors, we have a chance of kind of getting, to that scale in terms of coherence. All right. This is exciting, but there's a lot of challenges associated with going from, say, 10 to the 20 spins or 10 to the 18 spins of electron spin resonance rate down to just one spin and doing the same experiment with one spin. And all right, so hyperfine can be dealt with. Silicon's lighter. That means the spin orbit coupling is weaker. There's some trade-offs, and this is why single electron physics in silicon is hard. One big difference between 3/5 and silicon is that there's a valley degree of freedom in silicon that we need to take into account. Another practical thing that's important when you're making a quantum device is that small effective mass is your friend. And early experiments in indium arsenide, indium actinide, materials with a really small effective mass give you nice quantum energy scales, right? Because everything goes like 1 over mass, right? And so in silicon, the effective mass is significantly larger than in gallium arsenide or indium arsenide. And what that means is if you want to make a quantum device and see, orbital excited state energies that are reasonable, you need to make a really small quantum dot, a very small box for the electron to sit in. Otherwise, these energy scales are going to be, too small to resolve, even at low temperatures. And so this boring effective mass table has really occupied a lot of our time the past few years trying to figure out how to get around that problem. In the end, this is what worked. What we do now is we work with it's a silicon quantum well heterostructure. This is a transmission electron microscope image where we're kind of looking through the crystal from the side. And this is the top surface, and the substrate's way down here. The electronically active region of the device is a silicon quantum well. This is where the electrons in our dot are going to live. And they're trapped by a barrier on both sides, top and bottom, with a mixture of silicon germanium, it's an alloy. This is a quantum well. What's kind of special about the quantum well in terms of details is it's undoped. So in the absence of any gates on top, there are no electrons in this quantum well. It's kind of empty. To pull an electron into a quantum dot, you put an electron in a cage, on top of this substrate we fabricate called gate electrodes. And these just work, you think of it in terms of capacitance. You have a capacitor, parallel plate capacitor. C is epsilon, not A over D. Q is equal to CV. I have some gate. I put a voltage on it. I'm going to accumulate some charge underneath it. And that's how these gates work. These are called accumulation gates. And by adjusting the voltages on these gate electrodes, we can create single quantum dots in this silicon quantum well that's about 50 nanometers below the surface of the wafer. Okay. Is that kind of clear enough in terms of the overall physics, right? So one thing that's confusing is a lot of times people look at these gates and think the action is here, in this metal layer. The real electronic activity is down here in this quantum well, and that's about 50 nanometers removed from the surface. Right? So these electrons are protected. They're sitting down in the crystal lattice. They're not up top where these gate electrodes are. All right. In terms of scaling this up, we want to build a system that can be scaled at least in 1D. And show you the device architecture that we're thinking about now. It kind of has a repeating unit cell geometry where we have 3 qubits that are lined up in a row. And each set of 3 qubits is read out using a charge detector. So that's the rough idea. And the reason for doing this is that you can easily scale this up in PowerPoint and very nicely make a one-dimensional array of say 20 or 50 qubits. But in practice, it kind of works. In the laboratory, we've gone up to 12 dots now. This is a device where we have 9 quantum dots in a chain. underneath these red gates here. Each quantum dot is separated from its neighbor by these green called barrier gates that generate a potential between the two quantum dots. And then down here we have 3 charge detectors, right? So the picture is like 3 qubits per charge detector repeated in one dimension. Okay. Let's look underneath the hood and try to understand how this thing actually works. This is a simulation of the 2-dimensional electron density in that silicon quantum well underneath the gate electrodes in a quantum well. Okay, so same scale, and what we'd expect to see based on the simulation is if we tune the voltages on these gates right, we can create 9 potential minima and trap electrons in these quantum dots. That's like a spin chain that we're making across the device. And then for readout, we can use these charge detectors and measure the current or conductance through those charge detectors. Now, let's come back to the effective mass issue. It's about half a micron. And if we go back to when I was a young postdoc, this is the same device in gallium arsenide, but this is just 2 dots. And Elzerman's here, Delft device is very, very similar, right? And so you can see that we're now packing, due to the effective mass issue, this is not by choice, it's because we have to. We have to make very small dots in silicon. We have about 12 quantum dots in the same areas where we used to have just 2, right, at gallium arsenide. These are very small devices, and it takes good students to kind of get this off the ground. In terms of the qubits, silicon looks very nice. These are single spin Rabi oscillations. This is natural silicon. It's not even the isotopically enriched silicon. See Rabi oscillations that persist, out to tens of microseconds. And we've done very careful measurements. It's called randomized benchmarking to determine the fidelity of these gate operations. And you can first experiment with these devices better than 99%. Tarucha's group in Japan, there's also work from UNSW, have pushed the fidelity of these oscillations and isotopically enriched silicon beyond the 99.9% level. A really impressive level of accuracy for the single qubit rotations. The implementation of 2 qubit gates has been a challenge, I would say, based on these early devices. Due to the Hyperfine interaction, it was hard to do anything more sophisticated than exchange gates and single qubit gates. But now in natural silicon, you can see pretty high fidelity C0 gate operations that are just driven electrically. Okay. So this is all good news in terms of moving forward with the silicon device platform. All right. What I want to talk about is how we can couple the spin trapped in one of these devices to photons. How we can try to move away from this nearest neighbor coupling and eventually push the device into a regime where we can have coupling over long distances. And it's been a really nice project to be involved with. This is Xiaomi, he's a senior student in my group, and David Zajac. David mastered the fabrication of devices that look like this and like this. Xiaomi worked from the other side, in the early years of his PhD, and perfected the development of the superconducting cavities that we use to trap the photons. And in the past few years, they kind of put their heads together, and they built a nice integrated device architecture that combines the spin qubit with a superconducting qubit cavity that we can trap the photons in. And I'll be telling you about the work that these 2 students did for the next half hour. Okay. So let's zoom out a bit. This field started with what's called cavity quantum electrodynamics. The idea of this is that we want to look at the interactions between light and matter at the single particle level, not the mini particle level. And the kind of paradigmatic theme of this set of experiments is that you have a cavity that you can trap a photon in, and if that photon energy is matched to the transition energy of a 2-level atom or artificial atom, and you have an interaction between those systems, these 2 systems, the atom and the cavity, can kind of play a game of hot potato, right? Where if I start with the atom in the excited state, it can transfer that excitation and create a photon in the cavity. At a later time, the photon drives a transition from the ground state to the excited state, and you just move this excitation back and forth between the cavity and the atom as time evolves, right? Now, this is described by what's called the Jaynes-Cummings Hamiltonian. It's shown here. Here's a term that looks like h bar omega a dagger a. That's the energy of the photon in the cavity. And generally, they'll have a 2-level system that has some transition energy. This term here just describes the energy of that 2-level atom, depending on whether it's in the ground state or the excited state. And this is the interesting interaction term or hot potato term that describes how this excitation is transferred back and forth between the atom and the cavity as a function of time. Okay? Now, there are a couple of regimes to work in, but the interesting regime is where this coherent coupling rate, G, exceeds all of the loss rates in the system, right? We're never going to make a perfect cavity with perfect mirrors and light is going to leak out of the system over some time. But we'd like that process to be slow, and you want it to be slower than this interaction time, right? You'd like to have many quantum coherent interactions before the light leaks out, because that's the end of your experiment. The other thing that's important is that our qubits are never perfect, and that's why we're working on silicon. But we want a dephasing rate or an energy relaxation rate for our two-level atom. It's called gamma in this experiment. That's also slow. So good qubits, good cavities, small kappa, small gamma, and large interaction rates, large G's. That's what we want. G's called the vacuum-Rabi frequency. And what's neat about this field is it started off a long time ago in the field of atomic physics, like Harosh, Jeff Kimball, many groups, looking at interactions between a two-level atom and a microwave frequency cavity, and basically taking atomic beams and passing them through cavities. And what they learned in these early experiments is that in a well-defined system with high-quality cavities, you could actually see what's called a vacuum-Rabi splitting. And think of vacuum-Rabi splitting as I have two mechanical oscillators, they're oscillating, and now we couple them together with a spring. We're going to have a high energy mode and a low energy mode, right? And you have normal mode splitting associated with those two degrees of freedom kind of interacting with each other. And the splitting in the transmission through a cavity like this is a demonstration that in this experiment they've indeed kind of hybridized the quantum state associated with the atom with the quantum state associated with the photon in the cavity. That's the rough, high-level picture of what cavity QED physics is about. About a few years later, 10 years later, 15 years later in different fields, these are papers on self-assembled indium arsenide quantum dots. Cavity QED moved from the realm of atomic physics to solid-state physics. And I wouldn't say that this is quite obsolete, but it's pretty close, just based on things that can be done now in a condensed matter context. And so this is vacuum-Rabi splitting associated with tuning one of these indium arsenide self-assembled quantum dots through resonance with the cavity frequency, showing that you can indeed hybridize light and matter, in the solid-state system. Okay, so really beautiful experiments. So, in the context of this talk, why should you care about strong coupling, and why is it important? Well, one thing is that if we do this right, we can see Rabi oscillations associated with a quantum transition between light and matter. Usually we think of a Rabi oscillation as you drive a spin with a microwave field and you drive a transition from the excited state to the ground state and the spin just processes around, right? This is an interaction between light and matter, and so what we're doing is we're transferring a quantum excitation from the atom to the cavity and back and forth, right? So it's a different kind of oscillation. It's called a vacuum-Rabi oscillation associated with interactions with the atom and the light field. From a quantum information perspective, this is important because if we can show that we can transfer coherence from a quantum system to a photon, we can also use that photon to couple to another qubit that's placed in the same cavity. And in principle, this should allow us to have a long-range coupling mechanism between qubits. Okay. Let's dig in and talk about how we can do this now with spins and silicon. This is an optical micrograph of one of our devices. The scale bar here is about 1 millimeter. And what you're looking at is a patterned niobium film that's been deposited on a silicon substrate. And we're going to take a microwave signal generator, we're going to shine microwaves into this device, and we're going to measure the transmission, what comes out of the other side, and we're going to look at the amplitude of that transmission and the phase difference that a photon picks up as it goes through the cavity. Okay? That's a rough idea. Now, this is a complicated structure. It's hard to see from the back of the room what's going on here, so let's kind of simplify it down. Right? We're all familiar with the optical cavity. You take two mirrors and just base them off against each other, right? And by adjusting the length, you sort of set up a standing wave in this cavity. We want to do this in the microwave frequency regime instead of the optical regime because our quantum dots are lithographically defined, right? They're relatively large, and the energy scales associated with them are in the 10 or 100 microeV range, not the electron volt range, right? So much smaller energy scale. we need to go to lower frequencies. And so there are a number of ways to think about this. One would be, take a coax cable and cut it in half with a razor. There's a central conductor and there's a ground plane on both sides of the conductor. So what's happening here is the ground plane and the central conductor. We're now going to take the central conductor and cut it here and here, and we're going to set that length to be lambda over 2, half the wavelength of the photon that we want to trap. And these two capacitors that we've created by cutting the central conductor set the rate at which light can kind of leak in and leak out of the cavity. In theory, that should set the quality factors or the transparency of the mirrors. Is that analogy kind of clear? So, this is a complicated device, but really what this part is doing, this is a microwave cavity. We're trapping a photon between two mirrors. Okay. Now what we want to do is take this microwave cavity and embed our quantum device in it, our quantum two-level system. This isn't the 12-dot device, but this is just a simpler, it's called the double quantum dot. I'll talk about it in a minute. It's defined in silicon, and notice the scale bar here. This is about a half a micron, 500 nanometers. This chip's about a centimeter across. And one of the reasons that we're really excited about spins and semiconductors is just size scale. Superconducting transmon qubit might be 300 microns across on the side. A trapped ion system, usually you have an inter-ion separation that needs to be large enough that you can individually address with laser beams. Things get big, but these devices are really tiny, and you can pack a lot of qubits on the amount of real estate, right, that's shown on the slide. Okay. But let's start off with a simple demonstration of just one spin and one photon. Okay. Now let's dig into this and talk about the physics of what this device is. Now, if you forget about the quantum level and the gates, at the quantum level, this double quantum dot is described by this simple Hamiltonian. Right? So imagine that you have a double well system and you just have one charge in it. Depending on whether the potential is tilted this way, right, I can have the electron in the left dot. If I tilt it this way, it goes in the right dot. Okay. So those are the two quantum states. Electron on the right, we call that 0, 1. One electron on the right, none on the left. Or 1, 0, the electron's localized in the left dot. Okay. Now, if there's a tunneling rate that couples the left side to the right side, you'll see an avoided crossing. There's an off-diagonal term in this Hamiltonian that gives you avoided crossing. So this is like a textbook two-level system avoided crossing that you'd see in Sakurai or Koh-Tanuji or whatever quantum textbook you're kind of raised on, right? What's nice about the system that we work with is that this tilt parameter epsilon, we call it the detuning, that's really a gate voltage or a set of gate voltages on the device. If we just adjust the voltages on those gate electrodes, we can tilt our double well potential. This interdot tunnel coupling, TC, sets the magnitude of the splitting. This can be adjusted as well using gate voltages. So in practice, we have full control of the Hamiltonian, and all these quantities can be referred back to some voltage on the device. Okay. Good. Now what's a double dot? Another way to think about it is we have two islands that we're trapping electrons in. Due to the nanoscale nature of these quantum dots, there's a large electrostatic charging energy that we have to pay to change the electron number on one of these quantum dots. Generally what we'll do is we'll couple the double quantum dots to the outside world via source and drain electrodes. And if we want to change the electron number on the left dot or the electron number on the right dot, we have to adjust those gate voltages to pull electrons into the device. And what you expect to see is what's called the charge stability diagram. This is a plot of the number of electrons in the left dot, the number of electrons in the right dot, as a function of these two gate voltages, V right and V left. And as we increase the right gate voltage, we'll add electrons one at a time to the right dot. If we increase the left gate voltage, we'll add electrons one at a time to the left dot. I think what's pretty amazing is that this device is maybe 100 nanometers across, contains one electron, and it's getting buried in this chip that's about a centimeter across. And it's not at all obvious that a photon trapped in this huge cavity is going to care at all about anything going on at this length scale, right? Okay. So here's the theory prediction, and here's what we see in measurements. What we're doing is we're shining light in the cavity and we're looking at the transmission. This is the transmission as a function of the right gate voltage and left gate voltage. And hopefully you can see here is that there are parallel lines running down this way. These are associated with changing the electron number in the right dot. There's a parallel line here and a parallel line here where we're changing the electron number in the left dot. And what these data demonstrate at a basic level is that the transmission of light through the cavity is a function of what's happening with the charges in the dot. We can see single electron charging transitions by looking at the microwave transmission through this cavity. Okay? That means that there's some coupling, some sort, some electric dipole coupling between the charge and the quantum dot in the cavity field, the microwave field of the cavity. Okay. Next, how do we get into a quantum regime? What we're going to do is we're going to zoom in on a specific region of this charge stability diagram. These are called interdot charge transitions, and these are important because the total number of electrons in the double well is going to be fixed. We're going to work with the same electrons. We're either going to push them to the right or left, depending on the way the potential well is tilted. Here's an example zooming in on the 3-2, 2-3 electron transition. The total number of electrons in the device is 3 plus 2, 5. Here we have 3 in the left dot and 2 in the right dot. Here we've just tilted that double well potential and we moved one of these electrons over to the other side. Okay. What's plotted here is the transmission through the cavity as a function of these voltages. And you can see that there's a big cavity response here. The transmission through the cavity almost goes to 0 as we move that electron from left to right across the double well potential. And why is that? Can you have an intuitive picture of what's going on? So here's what I'd like you to imagine. You have your left and right dot energy levels, and the typical energy scale associated with a quantum dot is the charging energy, which is millivolts. The typical photon energy at about 8 gigahertz is about 30 microelectron volts, much, much smaller than a charging energy. So if the energy levels are detuned like this or like this, there's no interaction between the light and the electron because they're too far out of resonance. But if we adjust the level detuning and bring them into resonance, then this very small microwave field can force that electron to hop back and forth from the left dot to the right dot. And there's a very large charge polarizability at that special spot where the left and right dot energy levels are degenerate. Okay? That's what gives rise to this transition. And that's why you can see that single electron hopping back and forth in these measurements so clearly. Okay? All right, let's get back to the strong coupling. What do we care about? We care about G, the coherent coupling rate. We care about kappa, how bad the mirrors are. And we care about gamma, how good or how bad our qubit is. We can start to pick those off kind of one at a time. This is a detailed slide. I won't dig into it too much, other than to say by measuring the cavity transmission as we move this way and adjust our detuning parameter, we can use what's called input-output theory in this Jaynes-Cummings Hamiltonian to extract the coherent coupling rate between a single charge and a single photon. And in this device, that's on the order of about 7 megahertz. This is the good coupling. It's the quantum mechanical coherent coupling that we care about. It's the electric dipole interaction rate between light and that electron in the double quantum dot. Now we want to compare that to the loss rate through the cavity. We can directly measure that from the quality factor of our cavity. This device has a loss rate that's about 1 megahertz. It's good, it's less than our coherent interaction rate. And then we can also measure the line width of our atomic transition. And this was a surprise because 5 or 6 years ago we tried to do this in different devices made out of indium arsenide, and the line width was very broad. It was about 1 gigahertz or a few hundred megahertz. There's really no chance of really getting into this coherent regime. But with these silicon devices, we now have respectable line widths that are on the order of a few megahertz generally. And so we can end up in a spot where you can really see the vacuum-Rabi splitting, the interaction between a single electron and a single photon. What's plotted here is the transmission through this cavity as a function of the tilt of the double well potential and as a function of the frequency of the light that we're shining in the cavity. The bright spot here, this line, is just the cavity resonance frequency. You get a lot of photons through the cavity on resonance. What we want to see is if there's any interaction between the qubit and the photons in the cavity when we kind of bring those energy scales close together with each other so that we can have this coherent flopping back and forth. And what you can see is as we adjust the detuning and bring the qubit levels down, there's no void crossing here. This is maybe a little bit more clear. This is a situation where we've reduced this tunnel splitting so that the minimum qubit energy is down here below the cavity frequency. And the qubit actually sweeps through the cavity at this detuning and this detuning. And there you can directly see the dispersion relation of this charge qubit. Okay. So just to summarize, in case you got lost in details, this is the transmission through the cavity when the atom is far detuned from it, it just looks like a Lorentzian, like a driven harmonic oscillator. When we tune our qubit into resonance with the cavity, we see the normal mode splitting, which is a result of hybridization of light and matter. And in this regime, this device is coherent, and you can reach what's called the strong coupling regime. Okay, so far I've only taken you up to charge, right? Our goal now is, can we extend this to spin? Is there a way to actually couple the spin of that electron now to the photon instead of just a charge-photon interaction, which is maybe kind of obvious from the context of these old cavity QED experiments with atoms and masers, right? Okay. All right. So people have been thinking about this since the late 90s. There are a number of theory proposals of how you might hybridize spin in light. The approach that we're taking is to use a small micromagnet just fabricated by our quantum dot. And what this micromagnet does is it generates a field gradient. This field gradient means that the Zeeman energy, the energy splitting between spin up and spin down, is going to depend on whether or not our electron is in the left quantum dot or the right quantum dot. It's also going to cause the quantization axis of our spin to change a little bit when the electron's position moves. And you can go through the numbers back in the envelope kind of calculation. The coupling between a single spin and an electron that's trapped in a single quantum dot and a single photon is quite small. It's better than 10 hertz, but not by a lot, right? But if you have a double quantum dot and you move the electron in a large field gradient, you end up with a very large effective spin-orbit coupling, right? And this is the idea that we kind of set out to pursue here. Okay. Here's what the device looks like. It looks exactly like the previous device I showed you. There are a few kind of incremental changes. One detail, if you're interested in cavities, is that we've changed the impedance of this cavity so that it has a higher characteristic impedance. And what that does is it pushes up the charge-photon interaction rate so that the charge-photon interaction rate in this device is more like 40 megahertz instead of just 5 or 6 in the previous generation of devices. We have some filters here that prevent microwave photons from leaking out of the cavity through our DC gate lines that go to these devices. And from a physics perspective, the main change is that on top of the double quantum dot, we now have a micromagnet, just a thin film of cobalt. It's magnetized but in plane. And you can think of like a bar magnet with fringing fields going around it. We're putting our double dot right in that fringing field. So there's a very large field gradient. And this is massive, 10 Gauss per nanometer. It's big. It's a really big field gradient. All right. Well, what we expect to see, we can think about what would happen here with spin. Instead of adjusting the detuning of like our charge qubit, the energy scale that's important for spin is Zeeman, right? 5 minutes. So we're going to tune the Zeeman energy of the spin, and we're going to look for avoided crossings when the Zeeman energy is comparable to the cavity frequency. And this is what we saw in our measurements. There's a lot of the cavity transmission as a function of field and frequency. This is the cavity frequency, and as the field is increased, eventually the Zeeman splitting is brought into resonance with the cavity, and here you can see avoided crossing between spin and light in the device. Okay, so this is a direct observation of spin-photon coupling in this kind of system. This device has 2 double dots in it. There's one here, and there's one here. The data from the second device are shown in the insets. It's very similar. So it's pretty reproducible in terms of the overall way that the experiment works. Here are the figures of merits. The spin-photon coupling rate's about 5 megahertz. The decoherence rate is a couple of megahertz. The cavity decay rate's also a couple of megahertz. This gives us a cooperativity of about 7. But here you can see the vacuum-Rabi splitting. This is now a hybridization of spin and light, right? Not charge and light, but this is direct coupling between spin and light. Another thing that's cool about this is that since we're using a combination of electric dipole and spin orbit, we can turn this coupling off. And maybe there's a way to do this with ensembles by tuning your resonator out of the way and kind of decoupling that way. What we can do with our device is we can go from this double dot regime where the electron can easily hop back and forth between the double potential to a highly detuned regime where the electron's localized in, say, the right dot or the left dot. And in that single dot regime, the spin-photon coupling rate's much, much smaller because that electron's not really going to move much in response to the cavity field. And you can see the vacuum-Rabi splitting here is large. As we tilt the double potential, it gets smaller. And at this point, we can't see it. That's just with about 50 microvolts of tilt. So you can turn it on and off. All right? Another thing that comes out of this, and I'll just go over this quickly in the interest of time, is that when you have the spin-photon coupling, it very naturally gives you a way to resolve the dynamics into readout of single electron spin states. And the way this is conventionally done is by using what I call the Elzerman technique, where you couple a quantum dot to a Fermi sea and look at spin-dependent tunneling. Another way to do it is a singlet triplet readout. And these approaches are very destructive, right? If this electron spin is spin up, it hops out into a Fermi sea and you never see that spin again. It's sort of gone. And with the cavity QED approach, you can use the microwave photons to very lightly interrogate the electron spin state. And that's what we're doing in these measurements. We can resolve single electron spin Rabi oscillations using the transmitted microwave frequency field and do single spin detection at the single photon level with these hybrid devices, right? So this is really exciting in terms of what can be done for readout and measurement of quantum states. And in theory, this should be what's called a quantum non-demolition measurement, and that's something that we need to look into in more detail. But to first order, you can see Rabi oscillations with a photon field. So you can also do measurements. Let me just finish up. I hope I tell you a little bit about how the devices are made. There was a lot of work here that was swept under the rugs, but this is the hard part of the experiment, is actually getting these devices to play well. And then marry that together with the superconducting elements. You see charge-photon, strong coupling, spin-photon, strong coupling. What's next? Well, one thing I hope I want you to see is I think we're moving away as a community from kind of one-off qubit devices in silicon, right, where you have a magic killer device that you measure for a few years and kind of move on. We're making pretty complex structures now in terms of the number of qubits. This is a device set up to be a 9-qubit device. We're measuring one right now in isotopically enriched silicon back at Princeton. So it's an exciting time. There's a lot to do. It doesn't look so different from our partners and competitors that trapped ion array in terms of the device architecture, apart from the scale, right? This is a 2-centimeter device, and here we're packing all 9 qubits down in something like a micron long. Right? So the next steps for us, we're trying to characterize our 2-qubit gate fidelities. In parallel with the measurements I told you about today, we're also working on trying to physically shuttle spin through quantum dot arrays. And I think the next big step for the field is to show that we can actually use light to entangle these two spins that are separated by large distance. And I hope that happens this year or next year. We'll see. Depends on how things go in the lab. So with that, I'll thank you for your attention. These are the people who did the work. This is David Zajac and Xiaomi. Those are 2 senior students in the group. And Felix Boryans is kind of stepping up and taking over the project. We're always looking for good people. So if you like this kind of physics, come by. This is a day we went skydiving. If you're curious about what's going on there, a little group outing. They have these indoor skydiving things I can tell you about later. So thanks for having me. It's fun to be here.